Hello, this is Math Jazz from Almost Cool, and I'm here with a special Wednesday calculus live stream. Today we're going to be doing some hydrostatic force problems. This will be a short live stream, but I just have a few problems that I'd like to show you, and here we go. So, the first problem I'd like to do, we have, of course, a submerged, here's our body of water, and submerged inside of it is a semicircle. Looks like this. That's about as good of a semicircle I'm going to be able to make. This bottom side of the semicircle is going to be parallel to the surface of the fluid, which is water in this case. And what we know is that the distance between the bottom of the semicircle and the surface of the water is going to be 4 meters. And the distance across the semicircle is 12 meters. So how do we set this up? Well, first we want to get an equation that describes the shape of this semicircle, and we want it to be an equation that gives us the distance across when we're at a depth of x. So this semicircle is half of a full circle, the radius 6. Center is going to be at y equals 0, and x equals, well, 4. We're going to put the origin right there, in line with the center of the circle and on the surface of the water. So the center is going to be at x equals 4. A circle that has a center at x equals 4 and a radius of 6 has equation x minus 4 squared plus y squared equals 6 squared, which is 36, or y is equal to the square root of 36 minus x minus 4 squared. This is of the top half of the circle. Now what we really want is the distance across the circle, and this equation only gives us the distance from the midline to the top of the circle, or the right side of the circle. So we're going to have to multiply this by 2. Now this will give us, let's draw our diagram again. If this is the surface of the water, and here's our semicircle, and we are a distance x down from the surface, then y is the distance from this side to this side of our semicircle. Now, multiplying y by dx would give us a differential rectangle. It'd be dx tall by y across, and integrating that would give us the area of this plate. So we get 2 square root of 36 minus x minus 4 squared dx. If we were to just integrate this, we would get the area of the plate. That's not exactly what we want. We have to multiply by how deep we are. So if we are x deep, then we are x deep. That's why we chose to put the origin on the surface of the water. And since we're in meters, we multiply by the density of water, which is 1,000 kilograms per cubic meter, and we multiply by gravity, which is 9.81. And we integrate that from 0, which is the surface of the water, down to 4, which is how deep the plate goes. We don't worry about this region up here above the water. There's no hydrostatic force on that. I mean, there's the air is putting a fluid force on that, but we were asked to look for the hydrostatic force, the water force. Hydro meaning water. Or if we were asked for hydrostatic force with a different fluid, we would use that fluid, that liquid, but we're not doing gaseous pressures. Okay, so this is the integral that we need for the first one. Let's clean it up, pull out all the constants. 9.81 times 1,000 is 9,810 times 2. Then we have the integral from 0 to 4 of x times the square root 36 minus x minus 4 squared dx. This is our integral. The u substitution solves it nicely, and we will leave it like so. Okay, so let's move on to another problem. Actually, set up my screen a little better for that. There we go. So our next problem is going to be, we have the surface of the water here, of course. We have a square that is submerged. I'll call this diagonally. Sides are length A. And we need to calculate the hydrostatic force on this plate. So we're not told what units this is in, so this is going to be generalized. So that means that we'll get, instead of getting our nice gravity times density here, we're just going to write G for gravity and rho for density, and that'll be good enough for us. Okay, so we have to figure out an equation that gives us our differential volume element or our differential area element, depending on how far down we are. So if we were down a distance x, then what y gives us the distance across? Well, that's not so bad. We have two regions. One is if I go down x, then I have to also go across x. We have a right triangle there. So our equation is going to be y equals 2x, because for every x I go down, the distance this way is x, and the distance that way is also x. So the distance across is 2x. But that only works as far down as the halfway point. After that, I have a new equation that has to go the other way. So this will be y1 is equal to 2x. y2 is equal to, well, when I'm down a distance of x, I start off at 2x, but when I'm down a distance of 2x, I go to 0. So I have 2a when I'm down a distance of, actually, let's figure out what the lengths of these sides are. So if this side is a length of a, and these two sides are equal to each other on this right triangle, then we have the Pythagorean will give us that b, that'll be the distance from here to here on the right triangle. One of the legs of this right triangle is b. B squared plus b squared equals a squared by the Pythagorean theorem, or 2b squared equals a squared, or b is equal to a divided by the square root of 2. So y2 is an equation that starts here at a depth of a over the square root of 2 and goes down to 2 times a over the square root of 2. And our distance across starts at 2 times a over the square root of 2 and shrinks to 0. So what we want is, well, let's write this in slope forms. No, let's find a slope. Okay, so the slope, m, is equal to, we lose 2a over the square root of 2 as we go from here to here, because our length starts off at 2a over the square root of 2, or just 2a over the square root of 2 is equal to a times the square root of 2. The square root of 2 cancels on the top and bottom. So it starts off this big and shrinks down to 0. So we've lost all of that. So our difference in y is going to be negative a square root 2. And our difference in x between here and here is going to be, well, this distance here is a over the square root of 2. Get a over the square root of 2. And this means that these a's cancel. Dividing by a fraction is multiplying by its reciprocal, so we get negative 2 as our slope. Here's our slope. So y2 is equal to negative 2x plus, well, so we need to figure out what our y-intercept is. So when we plug in a value, well, no, let's use point slope form. That's easier. So y2 minus, the point that we know is that y is 0 here. So y2 minus 0 equals negative 2 is our slope times x minus, the x value down here is a square root of 2. Great. So that means that y equals negative 2x plus 2a root 2. This gives us the equation for the bottom part of this square. Okay. So we're going to need two integrals. The integral from x is 0 to x is a over the square root of 2. That's the top part here of the density of water times gravity times the depth times our differential rectangle, which is y dx. Y is equal to 2x dx. This will give us the hydrostatic force on the top triangular part of this square plate. Then we add to get the hydrostatic force of the bottom, we start from a over square root of 2 up to a times the square root of 2. That's this depth all the way down to this depth. And we get rho g x, so that's density, gravity, distance, or depth. And then we get our y2 for the length of our differential rectangle. Negative 2x plus 2a root 2. And then the height of our differential rectangle is dx. So this is the hydrostatic force for this plate. Now, it looks like there might be some cancellation if we multiply rho gx times negative 2x dx and combine that with this chunk here and then integrate. I'll leave that to you to do. Once we have this integral set up, it looks like it's just multiplying some stuff out and using the power rule on each chunk. Most of these are constants. Rho, g, and a, and square root of 2 and 2 are all constants, so this is a even though it looks fairly impressive and intimidating, since there aren't many variables, it's actually not so bad to take. Okay, so let's do another problem. Okay. So
Let's say that there is a milk truck carrying milk with a density of 64.6 pounds per cubic foot. And the keen-eyed among you will say, that's not a density. Density is mass over volume, and pounds are not mass, pounds are force. I like to call this a force density instead of a regular density. It actually is not so hard to work with. It's actually easier to work with, I think, than using a density and multiplying by gravity and all of that. But this is an example of a standard system problem. And it's also an example of a problem where the fluid isn't water, and so we don't get our usual 62.5 pounds per cubic foot in the standard system, or 9,810 newtons per cubic meter, which is the equivalent factor when you're using the when you're using the metric system. So we have this. We have a cylindrical tank, and we're looking at the hydrostatic force on the circular caps, the circular bases of the tank. So this is a circular base of the tank. The tank itself would look something like this. We're just looking at this circular cap on the end of it. So we have this milk tank. We want to find the force exerted by the milk on one end of the tank when the tank is full. We know that the tank has a diameter of 6 feet. So if this tank is full, I want to put the origin on the top of the circle so that when I multiply by the distance, well, I don't have to put it at the top. I'm going to put it at the top. That means that the center of the circle is 3 units down from the origin. So I get y squared plus x minus 3 squared equals our radius squared, so 9, which means that y is equal to the square root of 9 minus x minus 3 squared. This gives us, of course, only 1/2 of the distance across, so I'm going to multiply this by 2. So this is going to be the the width of our differential rectangle. So we get 2 square root 9 minus x minus 3 squared dx would be the area of a differential rectangle. Its depth is x because we chose 0x to be at the top. And then the weight density is 64.6. So the integral of this from a depth of 0 at the top of the tank down to a depth of 6 at the bottom of the tank, this gives us our hydrostatic force. I told you you didn't have to put the origin at the top of the tank. You can put it in the center of the tank. That would be fine. If you did something like that, then we'd have our circle like this. The equation for that would be y equals the square root of 9 minus x squared, because our origin is at the center of the circle. Now the distance across is still 2 times that. And then we'd have 64.6 times our depth. Well, our depth is going to be, this is x equals 0. And when x is 0, we are 3 feet below the surface of the fluid. So we multiply by x plus 3. And then we multiply by our differential rectangle, which is 2 square root of 9 minus x squared dx. We integrate that from the top of this, the surface of the fluid is at -3 because the origin is here, the surface is there. And then the bottom is going to be at 3. So this integral gives us the same hydrostatic force as this integral does. These will come out to the same value, and both are valid ways of setting up this problem. And if you notice, if you let u equal x plus 3, that means that x equals u minus 3, and du is equal to dx. If you do this substitution on this integral, you will get that integral. So one way of thinking about what a u substitution is it's just moving your coordinate system. Well, there are some trickier u substitutions than that, but when you're doing a u substitution where u equals x plus or minus a constant, that can be thought of as just moving your coordinate grid around for your integral. Okay, now I want to also do this same milk truck, but instead of having the milk truck be all the way full, let's have it be half full. So here's our the circular cap on the end of our cylinder, and this is going to be the surface of the milk. It's only a half full truck this time. How does that change things? Well, if we have this setup here, all we have to do is integrate from 0 to 3 of the same integral. And that'll give us the hydrostatic force we're looking for. Because now instead of going from -3 up here all the way down to 3 and getting the hydrostatic force on this whole circular region, we're only integrating from 0 to 3, and we get the hydrostatic force on that region. Likewise, going up to our other integral here, we can integrate, instead of going from 0 to 6, we can go from 3 to 6, because in this diagram, 3 represented this halfway spot on the cylinder, and integrating from 3 to 6 will give us the hydrostatic force just on the bottom half of the circle. So one of the nice things is that once you have an integral set up, it's very easy to tweak the endpoints to get the hydrostatic force in particular places on whatever you're trying to measure the hydrostatic force on. So that's not so bad. Okay. Let us do one more. So let's say that we have submerged at 10 meters below the surface a semicircle with a 4-meter diameter. That is, here's the surface, here is the center of our half-circle plate. It is 10 meters below, and the diameter is 4. Now, I like to put the origin at the surface of the water. You can really put it anywhere you like, but let's put it at the surface of the water. That means that this circle here has its center at x equals 10. So we have y squared plus x minus 10 squared equals our radius squared. Well, our radius is 2 because our diameter is 4 and our radius is half of that, and we square that and we get 4. So our equation for our semicircle is y equals square root of 4 minus x minus 10 squared. That gives us, of course, just this distance halfway across the semicircle, multiply by 2 to get the full distance across, and now this becomes the width of our differential area element, our differential area rectangle. So 2 times the square root of 4 minus x minus 10 squared dx, that's our width of our differential rectangle times the height of our differential rectangle. We multiply that by the depth, which is just x, and we multiply that by the density, the weight density of water, which is going to be 9.81 times 1,000. 9.81 is gravity, and 1,000 is the density, so we'll just multiply that out to begin with. We get 9,801 newtons per cubic meter. We integrate that from, well, the top of our circle is when x equals 8, and the bottom of our plate is when x equals 10. There we go. And that is all I have planned for today. So I hope that you're enjoying using calculus, learning calculus, and I am trying to increase the number of times that I do calculus live streams. In a few weeks, I'm going to get back to making tutorial videos, I hope, but I'm going to start trying to do 2 or 3 live streams a week. The one on Monday will remain as scheduled, but the other ones will probably happen, well, let's say that as I figure out what times work best for me, I will set up a schedule for them. Until then, they'll happen sporadically through the week. But again, hope that you're enjoying calculus, and I hope that you're enjoying learning calculus, and I hope to see you next time. Bye, and thank you.